Now we're going to take a deeper look at binary operations, and in particular how they affect a set we're going to call Zn. So we're going to in particular look at the issue of a binary operation being well defined. So we're going to review some of the concepts related to congruence classes that we've seen on previous videos and some of the previous exercises. We're going to define what Zn is. We're going to review the definition of binary operations that we had in the last video. And then we're going to think about some possible issues that binary operations can have with respect to being well defined, particularly on sets like Zn. And again, Zn will be defined later in the video. All right, so let n be a natural number. The congruences modulo n are the sets of numbers that are congruent to each other modulo n, right? They're the elements of the same team, and same team meaning they're congruent mod n. And of course, we define them more precisely in this way. If n is a natural number and a is an element of the integers, then the congruence class of a modulo n is denoted by bracket a sub n, and is defined as bracket a sub n equal to the set of all integers x, such that x is congruent to a mod n. And we can think of a bracket a n as the congruence class modulo n, or the team, that includes the number a. In other words, a is on the team, and we're looking for all its other team members. So here are some properties of congruence classes that we proved in the last video, or previous video, not in the last video, a couple videos back. So again, n is a natural number, let a and b be integers, and we define bracket a equal to the set of all integers x, such that x is congruent to a mod n. That's just a reminder from the last slide. So another way of saying bracket a is it's all the set of all the integers x, such that x equals a plus kn, where k is an integer. We have this condition for when congruence classes are equal. They're equal if they're precisely when their representatives are congruent mod n. This tells us when two congruence classes are not equal. If they're not equal, then they don't share any elements. Their intersection is empty. And finally, if we take the union of all the congruence classes represented by 0 through n minus 1, that gives us the set of all integers. Now, one of the nice things about that last result in 4 is it tells us what a complete list of the congruence classes is. And in particular, it tells us that there are finitely many. We start at 0, we go to n minus 1. That is n congruence classes altogether. So we let n be a natural number, then we define the set Zn to be the set of all congruence classes starting at 0 and going through n minus 1. So let's see what happens when we try to define a binary operation on Zn. It actually makes sense because we have all these binary operations on integers. Why couldn't we have a binary operation on those congruence classes? Let's see. Binary operations means we have two inputs, we have one output, and we can define it in any way that we want as long as it makes sense. Right? So we define a binary operation on Z4. We're going to do that one. And we're going to call it star. That's going to be the operation. So if I have bracket A star bracket B, that's going to equal, and it's going to be a pretty nice rule, but it's going to depend on what A and B are, right? So remember, I'm going to think of bracket A as the first congruence class, and bracket B is the second one. So our result is going to be the first congruence class, bracket A4, precisely when we add A and B together and get a multiple of 3. And then if that is not the case, then it's going to be the second one, the bracket B, otherwise. Right? So if we add A plus B and get a multiple of 3, we take the first one. If we add them and get not a multiple of 3, we take the second one. So looking at an example, if we do bracket 1 and bracket 2, that's going to be bracket 1. Might have to think about that, but if you add the 1 plus the 2, you get a multiple of 3. You get literally 3. That means you choose the first one. That is bracket 1. And then if you do something like bracket 2 star bracket 3, once again, you have to, we're going to end up with bracket 3 this time, and the way you get that is you add the 2 and the 3. That gives you 5, which is not a multiple of 3, so you choose the second element, bracket 3. So the question is this a binary operation on Z4? Well, let's see possible issues, right? The first thing is there are two inputs and one output. That is consistent with being a binary operation. The inputs and outputs are all in Z4, so you don't have any closure issues. It looks like your domain is the set of ordered pairs with elements of Z4. Your outputs are elements of Z4. What's the problem? Well, there is one major issue that we have to think hard about. So if we took bracket 1 star bracket 2, we figured that one out already. We add the 1 plus 2, we get 3. It's a multiple 3, so we choose the first one. And this is a different computation. We didn't do this one last time. But this one, if we do bracket 5 star bracket 6, now we add the 5 plus 6. 5 plus 6 is not a multiple of 3, so we're going to take the second one, that is bracket 6. And that may look fine to you, right? Oh yeah, because 5 plus 6 is not a multiple of 3, just FYI. That may look fine for you, but actually, bracket 5 and bracket 6 are our other congruence classes in disguise, right? 1 and 5 are congruent mod 4, which means that bracket 5 is equal to bracket 1. Also, 2 and 6 are congruent mod 4, which means that bracket 6 equals bracket 2. And that's both those bracket 6, both the one on the left-hand side of the equation and the one on the right. So if we rewrite that second equation above in terms of 1 and 2, that says that bracket 5 is bracket 1, bracket 6 is bracket 2, so bracket 1 star bracket 2, and that last bracket 6 on the other side is bracket 2 as well. So what happened is we did the same computation twice, bracket 1 star bracket 2. The first time we got bracket 1, the second time we got bracket 2. It means we got two different outputs. That means our star operation is not well defined, because one of the issues with a function is you can't have one input that has two different outputs. And we just showed that in the definition we gave of this star operation, that is exactly what happened. That means it also is not a binary operation, because binary operation has to be a real function. So I just want you to treat this as a cautionary tale. Anytime you are in a situation, literally anytime when you have multiple ways of representing the elements of your set, like here we have multiple ways we can choose the representative of our congruence classes, you're always going to have open up yourself to a possibility for a given binary operation not to be well defined. That doesn't mean all binary operations are well defined. It's just we have to be careful to see whether or not they actually are well defined. All right, so now that you have those issues under your belt, you're going to look at some more activities on binary operation. The PDF file is called More Binary Operations, and it's included with this video.